Well, good afternoon, everyone. My name is Arthur Carty. I'm the Executive Director of the Waterloo Institute for Nanotechnology. Today, the Waterloo Institute for Nanotechnology is hosting one of the world's foremost solid-state and materials chemists, Professor C.N.R. Rao, National Research Professor and Linus Pauling Research Professor at the Jawaharlal Nehru Center for Advanced Scientific Research, and it is my honor and pleasure to welcome and introduce him. One of India's most decorated and respected scientists, Professor Rao, has contributed enormously to the synthesis and structure property relationships of materials as varied as the two-dimensional oxides, for example, La2CuO4 or lanthanum cuprate, and the astonishing new nanomaterial graphene. His oxide work has had a major impact on our understanding of properties such as high-temperature superconductivity and giant magnetoresistance. Professor Rao has been honored by all of the major academies in the world and has received honorary doctorates from 49 universities. The two latest ones were Oxford and Liverpool this year, I believe. And with 1,400 published papers and 41 books to his credit, Professor Rao is the epitome of a prolific scientist. Needless to say, he has an enormous number of prestigious awards to his credit, from the Royal Medal of the Royal Society of London to the August Wilhelm von Hofmann Medal of the German Chemical Society, which he received this year. His recent work on the electronic structures of graphene and nanotubes is brought into focus by the award only last week of the Nobel Prize for Physics to Andrei Geim and Konstantin Novoselov of the University of Manchester for, and I quote, groundbreaking experiments regarding the two-dimensional material graphene. We'll hear more about the physical properties of graphene in his lecture today. Professor Rao's contributions, however, go far beyond research, reaching into science, advice, and policy. He is currently chairman of the Scientific Advisory Council of the to the Prime Minister of India, and previously served Prime Minister Rajiv Gandhi from 1985 to 1989, and the Union Cabinet from 1997 to 98 in the same capacity. As chair of India's Nano Mission Council, Dr. Rao has played a significant role in the accelerated growth of nanotechnology in India over the past few years. So please join me in welcoming a truly remarkable scientist, Professor C.N.R. Rao. Thank you.
Professor Carty, thank you so much for your kind words. I'm very happy to be here in Waterloo, of which I have known much. I have always considered Waterloo to be something approaching MIT in Canada, though it has some ways to go yet. But it's a great university that I know, particularly in engineering and science. Today, I had a choice of many possible topics, but I decided to talk on nanocarbons without knowing that there was going to be a graphene Nobel Prize. I didn't know that graphene was going to get a Nobel Prize. Though prematurely, I think it deserves it, the subject. I'm going to talk about nanocarbons because what it tells us is how subjects like chemistry, physics, electrical engineering, and a whole bunch of subjects come together in confluence to make this subject very exciting. I'm not going to talk about the engineering aspects. I'm going to talk about my work, which mainly deals with physics and chemistry, or chemistry and physics of these materials. For those who may not know much about my work, I thought I should spend 1 minute on what I have done all my life. For those young people, let me tell you, I have just started my 60th year in research. I started my research actually early 51, so in very few months I'll be starting my 60th year in my doing research. And what are the areas I've worked on? Most of my work has been on transition metal oxides, particularly metal insulator transitions, superconductivity, colossal magnetoresistance, and in the last few years, I do a lot of work on multiferroics and magnetoelectrics. This is still a very important area of my research. then I do work on not inorganic materials, but not organic materials, but inorganic organic hybrids to design new kinds of materials with fascinating properties. For example, the Kagome lattice. I have made variety of Kagome structures where with using different types of metal ions, I can fight the magnetic frustration in these materials in some way. So that type of work I do. And then in nanomaterials for the last 20 years, we have been working on zero-dimensional nanocrystals, one-dimensional nanotubes and nanowires, and also and two-dimensional nanofilms, particularly graphene. Today, of course, I'm going to talk about carbon-based materials, mainly nanotubes and graphene. Well, graphene, of course, is a simple two-dimensional layer. It is what we might call a mother of all graphitic forms. Because using graphene, you can make a buckyball, a zero-dimensional C60, for example, or roll it and make a one-dimensional nanotube, or you can stack it and get three-dimensional, get graphite. So the graphene, therefore, is sort of a mother of all these kinds of carbon forms. Just to remind you, the first carbon that really amazed us was in 1985, when my very good friend Harold Kroto and others, Smalley and others, discovered C60. C60 is this icosahedral, this kind of a spherical molecule with 5-membered rings and 6-membered rings. And there are 20 6-membered rings and 12 5-membered rings with unusual properties. And the most important property, please don't forget this. I'll use this later. I won't use Fullerene, but love of electrons. You put C60, you can pick up electrons like mad. You can put as many as even 10 electrons, but 6 electrons very easily. C60, 6 minus. But 3 minus is very important. C60, you put 3 electrons in C60. The salts of C60 with 3 electrons are superconductors. I hope you all know that. Or I can put a powerful amine with C60, just 1 electron to C60, I can make it a ferromagnet. It's a very, very amazing molecule, C60. I'm not going to talk about that. I'm just reminding you of the birth of nanoscience. In many ways, started with birth of this molecule in 1985. Though it was made in the laboratory only in 1990. 1985 was a discovery based on a mass spectrum, but 1990 it was made in the laboratory. Carbon nanotubes, on the other hand, were properly characterized only in 1990. Well, it is a very sad story. I'll mention it in a minute for the benefit of young people here. It is nothing but a tube which is obtained by rolling a sheet of graphene like this, and depending on the way you roll it, you can get different types of nanotubes. We can define a nanotube in terms of this equation where you have these chiral vectors and the chiral angle, and these chiral vectors, these coefficients n and m define the kind of nanotube you have. For example, when n is equal to m, we get an armchair nanotube. Where m is equal to 0, you get a zigzag nanotube, and so on. But under some conditions, for example, for m minus 1, n equal to 3r, you get a metallic nanotube. So when you make carbon nanotubes in the lab, particularly single-walled nanotubes, you get a mixture of metals and semiconductors. That is a big challenge, how to separate them. I'll come back to that towards the end of my lecture as one of the important things. In fact, when nanotubes were discovered, for those who may not know the history, it's very amazing. It was actually made by a very good friend of mine in Japan in the year 1976. He even described them fully, endo. Nobody noticed it. In 1990, my other Japanese friend, Ijima, described it beautifully with the electron microscope, pictures and so on, but everyone calls nanotubes as a discovery of Ijima, but endo is never mentioned. It's unfortunate. For those of you who would make a major discovery, make sure everyone knows about it. Okay. But anyway, lots of synthetic methods are there. Today I'm not going to talk about the synthesis of nanotubes. There are all kinds of special nanotubes, junction nanotubes, and so on, people have made. And or double-walled nanotubes. For example, here is a double-walled nanotube. The reason I'm showing that is you can make all kinds of nanotubes, single-walled nanotubes, double-walled, 2 walls there, and you can use a special catalyst, and you can even dope these nanotubes. This is just to show that all these materials can be doped. Carbon nanotubes can be doped with boron and nitrogen, make them p-type or n-type nanotubes. all this has been done. And today I'm not going to talk about that. I'm trying to remind you that this kind of thing has been done in the last few years. In fact, these boron-doped, nitrogen-doped double-walled nanotubes were made in my laboratory just about 3 years ago, 2007. Now, what is important is how to look at these nanotubes. Since a lot of young people are there, I hope you don't mind, I'll make it a little bit of a classroom lecture here. Characterization is extremely important and even difficult in carbon materials. What are the signatures of nanotubes? Which are the signatures we'll use to understand nanotubes? The most important is Raman spectroscopy. Being an Indian, I'm very proud of that, because Raman spectroscopy, without that, you are nowhere in carbon nanotubes. You cannot characterize a nanotube without a Raman spectrum. The Raman spectrum has this big G band. The G band is characteristic of any sp2 carbon. Even benzene has sp2 carbon, therefore it gives you 1600 or 1550 band. That is nothing but a tangential mode, which is the G band in all sp2 carbon and also in the nanotube. What is more important is the small bands here at low frequency. These are the so-called radial breathing modes. You have a nanotube which breathes. When the nanotube breathes, that frequency of the breathing mode is inversely related to the diameter of the tube. So that is a very important thing, again, characteristic of the nanotube. The most important feature of this G band is I can use that G band to say whether something is metallic or not metallic, semiconducting or metallic. And it's very, very sensitive to the electronic structure and various things you do with the nanotube. So this G band and the RBM bands in the Raman spectrum are very, very important for characterization. Another important characterization, again, which I'll be using later, is the electronic spectrum, or it's really near infrared and visible region. For example, this is in electron volts, don't worry. Here, this metallic band here, there are characteristic band due to the metallic species, around 500 or 600 nanometers, and around 1,000 nanometers here, there are bands due to the semiconducting species. And these are all arising because of the so-called von Howe singularities in the electronic structure of nanotubes. So we'll be using this quite a bit to understand whenever we deal with nanotubes. Now, 2 words about graphene. Since my lecture is on nanotubes and graphene, graphene, as I told you, is this 2-dimensional sheet with all these ripples there. These corrugations come naturally because of thermal fluctuations and so on. And this is a really 2-dimensional system. And for those who may not know, historical admittedly, as long as 50 years ago, 60 years ago, I have a very dear friend in MIT called Millie Dresselhaus. He's an outstanding scientist. Millie Dresselhaus did some wonderful calculations when he was a very young girl 50 years ago, but nobody looked at that. There was no way to check these calculations. Experiments were not there. Today, of course, we know a lot about graphene, and we can check all the theory, and we can do more theory. So the real problem, however, synthesis of this is very difficult. How do you just pick one layer of a graphite crystal and do a study on that? Of course, the reason it became important and why they have given a Nobel Prize is not because a single layer of graphene has been lifted off the crystal, because of its unusual properties. What these people show, the Novoselov and Geim, that the energy of the electrons in graphene is linearly dependent on the wave vector near the crossing points of the Brillouin zone. That is one thing. And it also shows ballistic transport of electrons. Ballistic transport of electrons in solids is a very unusual phenomenon, and that happens here. More than that, it also shows quantum Hahn effect at room temperature. Normally, quantum Hahn effect is found at very, very low temperature. It's very difficult to find at room temperature, but this solid shows that. So that's why this solid became famous the minute it was discovered. What did they do? Well, I'll tell you how did they do that. They took a crystal. How do you get a single layer? They put a Scotch tape and just lifted off the Scotch tape. And the Scotch tape, just the top layer of the carbon atoms got stuck to the Scotch tape, and they put that on a substrate and studied it. Of course, we have done a lot of that at home. Someone like me should do that, because I put a lot of pressure and get a lot of layers come. Delicately, a very nice young girl should come, very delicately touch the crystal and lift it. I'm useless for lifting off one layer, because I lift off 5, 10, 15 layers. I'm no good. But my students are very good. They're very delicate. So we can lift off one layer. And that is what these people did. They lift off one layer, and then you get a single layer, or you do it, you can even get a bilayer. And then you can take those things and do atomic force microscopy. You can measure the height of that layer. If it is 0.4 nanometer, it is one atomic layer. Therefore, it is single layer graphene. If it is 0.8 nanometers, it is two layers, it is a bilayer graphene. Well, once it was done, you can do all the characterization. This is from the early work that came in the Proceeding National Academy of Sciences in 2007, just 3 years ago. You can see the single layer, two layers, you can get two lines. And look at this one. That is very nice. When they made it, if you put this single layer graphene on certain silica substrate, 300 nanometer silica substrate, very easy to make in the lab, it is transparent. You can actually see through it. In fact, that is how I know when my students have made single layer labs, I can look through it and see whether they made it. It's actually transparent, one layer graphene, okay? That one. And of course, you can measure the height of that. You can study atomic resolution using scanning tunneling microscopy. You see every atom you can photograph using scanning tunneling microscopy. Okay, again, you see, Raman comes again. See, Raman is something that is so powerful today in science of materials, particularly in carbon materials. In graphene, there is no other spectroscopic signature. You see, we had, in the case of nanotube, we had two signatures. One was Raman, another was the electronic spectra, electronic transition. You could see that. Here, there is no electronic band of graphene worth mentioning. So this is very interesting. You see, a single layer graphene gives a G band, which is not very intense. You see, that is the most primary band of graphene, sp2 carbon, the sp2 carbon vibration, skeletal modes, tangential mode. But look at this overtone, this whopping intensity. My God, I've never seen such a spectrum in my life where the so-called overtone, which would be very weak, comes huge intensity. Every fundamental band comes with a weak intensity. That is why the beauty of Raman is fantastic. Because the theory of this Raman is the so-called double resonance phenomenon. Today I'm not talking about the theory and what happens here is responsible for some of these things. You see, this is the 2D band, G band. The so-called defect-related D band is very weak in single-layer graphene, and this is very important to characterize it. I told you the problem is you cannot make graphene by Scotch tape, taking it one layer. You go on taking one layer at a time. Suppose you want 1 gram of it. How many times do you have to do that to get one Avogadro number of carbon atoms? And somebody calculated in America in physics today with a very few, somewhere, that's funny article, somebody said, for 1 gram it will cost about $60,000. I don't think anybody is prepared to pay $60,000 for 1 gram of graphene. So obviously, you have to make it differently. That is where I got into the act some years ago. Not 2 years, about 4 years ago, 3 years ago. Lot of methods. The simplest and the most important method that people use is the chemical method. Take graphite powder, cook it in an acid with an oxidizing agent, make graphite oxide. And graphite oxide can be very easily exfoliated by thermal shock or mechanical sonication. And then you reduce that and you can get graphene. Of course, that will be in solution. But you can't take it as a solid. That is the problem. You can take the solution, put the solution on any substrate, you get a graphene layer. Okay? But you can't call it graphene, you see. It is actually reduced graphene oxide. Because there are few oxygen functionalities will be still on the surface. It is not pure graphene. The Bangalore method, one of the methods discovered in Bangalore about 3 years ago, I don't even remember when, about 2 years ago, was this arc discharge method. I can make, by arc discharge, 2-layer, 3-layer graphene always, but not single layer. But it's good enough. 2-layer, 3-layer is as good as single layer for many applications, for technology and many engineering applications. I may say something about it later. Well, I'm sure you will not be able to see it all, neither am I going to read it out. There are a whole bunch of methods. For those interested, I have a recent perspective in Journal of Physics Chemistry Letters, 2010, where I have discussed these things. Single-layer graphene can be made by mechanical cleavage, I told you about, CVD on metal surfaces. But the trouble with single layer is you can't take it out. It has to be on a substrate. The minute you take single layer, it all becomes graphite again. You can't take it out. So that is the problem. Okay? But recently, I've just added yesterday, before I came, a day before yesterday. You know what we found? You take this graphene oxide. There are papers in Science and Nature saying this, take this single layer graphene oxide, reduce it by a vapor of hydrazine or something. Man, who wants vapor of hydrazine in a good engineering or a physics lab or even in a chemistry lab? It's all terrible. I didn't like it. So I was amazed when we found this one. What we find is you take graphene oxide, it's yellow, brownish yellow in color. We just put in sunlight, it becomes graphene. In fact, sunlight is too slow, so you can UV light faster. Don't do both of them. Take a good laser, excimer laser. It takes in 1 second. You take a laser irradiation in 1 minute. I can convert single layer graphene oxide to graphene, and that is the best way to produce by a laser method. And this is what I am advocating in the last 3 weeks. I didn't know that 3 weeks ago, but last 3 weeks and I've given you why it is formed here, what the technology, what the mechanism is. And of course, if it is not one layer you want 3 layers, 4 layers, there are many methods, particularly the arc discharge method I told you that we did in Bangalore is very important because it does not have any impurities, pure graphene. There's no oxygen, nothing, and it's all in gas phase, vapor phase synthesis. Therefore, you get very nice graphene, 2 to 3 layers, which is good enough for many applications and many of the studies. And that is enough for synthesis. As I told you, whatever you get, it is just a summary slide. You first do Raman spectrum. Don't forget, any paper that I get in this area without Raman spectrum and atomic force microscopy, I don't accept it because you must do those to characterize graphene, okay? So you do atomic force microscopy, measure the height, and if possible, transmission electron microscopy. You see here is something we made with 4 layers. You can see the 4 lines there. So you can measure TEM. And as a chemist, or even as a chemical engineer, some of you will understand one more technique was required to characterize. This is where we started doing that about 2 years ago, 2008, 2 years ago, is measure surface area. The area of a surface of graphene is theoretically predicted to be 2,500 square meters per gram, very, very large. Of course, nobody can make it. Nobody can measure it because it is a theoretical surface area. But all the surface areas we measured on experimental samples, actually 800 to 1,800 square, very large surface area graphene we can make in the lab. We can study many of the adsorption properties. Surface area is a very important characteristic as well. Okay. A few properties of graphene I'll summarize, which I have just added a couple of days ago since I was giving a summary lecture. You know, you may not believe this. 50 years ago, in fact, Millie Dresselos was telling me, I didn't know that. She was telling me in MIT when I was there a month ago. Many people thought, is carbon a magnet or not? Is carbon a ferromagnet? This is a question people have worried about for a very long time, old literature. Because many people found graphite was showing some magnetism. Of course, people said it's all due to impurity, of course, all kinds of things in graphite. So now I have graphene, I can see whether it is actually magnetic or not. Well, this is something I'm not going to discuss too much. I wanted to know, doesn't matter how I make graphene, how much trouble I take to purify it, whatever you do, I cannot avoid getting magnetic hysteresis. There's no doubt all graphene samples are weakly ferromagnetic, weak magnetism. Why does it come? It is because the lone pair orbitals all around the graphene, in the middle you have got the carbon sheet, the 6-membered rings, that will be antiferromagnetically coupled. So you have an antiferromagnetic background surrounded by these ferromagnetic lone pair orbitals. And in fact, now there are 3 theory papers which refer to our experiments as well, who show that why it should be ferromagnetic, etc. So there's a lot of theory on that as well. But anyway, they're all weakly ferromagnetic in terms of magnetic hysteresis. And another important thing, since many of you are engineers, what about mechanical properties? We find it is not as good as carbon nanotubes. When you put graphene in polymers, it does increase the elastic modulus and hardness of the polymer. Mechanical properties are also improved. What we found, we have a paper in Proceedings of National Academy of Science, PNAS, in Washington, in December issue, where we didn't do that. We took a very small amount of graphene, add a very tiny amount of carbon nanotube, 2 of them, but it's 2 nanocarbons at the same time. The minute we did that, we found an unusual synergy, extraordinary synergy in mechanical properties, where you put 2 nanocarbons, very small amounts, and for whatever reason, which I will not again go into today, There are these amazing properties. Graphene and nanodiamond, graphene and nanotube together give you extraordinary synergy in mechanical properties. In fact, somebody wrote about it in Nature. They wrote an article on our work, and our magnetism also. Nature wrote I never published in Nature. I never published in Nature and Science. There's a lot of waste of time waiting for the referee reports, and then usually they don't referee properly anyway. So best is to publish in professional journals, and if Nature wants, they can write about it later. It has happened to me all the time, so I advise young people not to waste too much energy waiting for a Nature referee report. And what happens is young people in Bangalore or anywhere, they publish in one Nature, publishing, my God, they work hard. Eventually Nature comes out. After that, 3 years they take leave because they're exhausted. So I think it's very bad. So I have to work all the time, so I can't afford to take rest. So the reason I've told you is this, when the Nature, they wrote it as world's lightest and strongest material. There's no doubt. It's the lightest and strongest material you can make with graphene and carbon nanotubes. Okay. There are many other properties. I'll not be talking about that. We can make wonderful transistors with graphene, with ambipolar properties. You can make very interesting, use this is what was made in our laboratory, these transistors. You can do all kinds of applications of the transistors. What is interesting again is coming back to chemistry. Any nanomaterial you make must be functionalized. I hope you all know that. You can use the solid up to a point. If you want to make a composite, you want to use some other thing, you have to disperse it somewhere, you have to put it in a solution. So today in my lab, which I wouldn't have known 5 years ago, you can give iron oxide or titanium oxide, anything I can solubilize in any solvent you want. I can give a benzene solution of iron oxide or benzene solution of titanium oxide, which is unknown. If you had asked me 5 years ago, I would have said, I called you mad. I mean, it's impossible, I would say. But it's not so. You can do all that. And the same thing applies to graphene. Just like, as you know, in carbon nanotubes, we functionalize carbon nanotubes in various ways. Same methods can be used. You can covalently functionalize them or non-covalently by wrapping graphene with a lot of all kinds of molecules with pi-pi interaction and so on, or chemically transform it and make solutions of graphene in any solvent you want. The trouble is, about covalent functionalize, you functionalize too much, you lose the electronic structure. You have to decide. These are all things you should know. Suppose you are interested in the electronic property of a nanotube or graphene, you should not covalently functionalize too much. Otherwise, you are pulling out electrons, forming chemical bonds, the electronic structure, too many chemical bonds, so electronic structure will be affected. So you have to use the right balance in how much covalent functionalization is allowed. The fact is that you can do that. But now on, I will talk a bit more about research, a bit more technical. I hope you don't mind. Some time ago, there was a paper from Cambridge, along with one of my co-workers, Ajay Sood, where they took graphene and you made a transistor, a top-gated transistor of graphene, and doped holes and electrons. When they doped holes and electrons, they started seeing the Raman band, G band, and Raman 2D band. The summary is here. The summary is the G band, whether it is holes or electrons, the G band started decreasing. That is, the band stiffens. There is no softening of G band, only the stiffening of the G band, frequency increasing, both with electron doping and hole doping. And they made a big fuss about it. Amazingly, they did publish in Nature Nanotechnology. I thought it's okay, it's interesting, and I started looking at the same problem slightly differently. Why not? Electrochemical doping has certain advantages and disadvantages in a transistor. Why not do chemical doping, just like we do in semiconductor physics? In semiconductor electronics or physics, we dope silicon with some other element, right? Same thing, why not do it? Just like I had shown you in the case of nanotubes earlier in my introduction, we could dope graphene using our gas phase method, both with boron and nitrogen. How do you know how much you have? We do electron energy loss spectroscopy in the microscope. This is unfortunately XPS is not very good. You have to do yields in the electron microscope, and we could estimate how much nitrogen and boron. Well, ignore all the spectra, that is not important. What is important is here, the curve, the amount of nitrogen, that is N doping, amount of boron, P doping, both again increase the G band frequency, stiffening of the G band. This to me was a surprise. Why is it when the electrons and holes with different types of carriers give the same effect on the Raman spectrum? So I was wondering about this. Then we did a new study This has caught the attention of a very large body of scientists. I'm going to spend 5 minutes on this. You know, I'm a chemist, so I want to do with molecules. I don't want to do with the big circuits and all that. You put a molecule and donate an electron or donate a hole. How do you do that? You can put an electron withdrawing molecule on a graphene surface. It'll be donating holes, withdrawing electrons from graphene. Or put an electron donating molecule, then it'll be donating electrons to the graphene. So I thought of studying that some time ago, about 2 years ago. Well, this is a crude slide. This is a G band. I put aniline, which is the electron donor, and nitrogen. When I put nitrobenzene, the frequencies start increasing. When I put aniline, the G band frequencies start decreasing. So opposite effects of molecular interaction doing N-type and P-type doping. The same, much more effectively, when I put molecules like tetrathiofullerene is a very powerful donor, tetrathioethylene, very good withdrawing group. So tetrathioethylene increases the frequency C, and tetrathioefullerene decreases the frequency of the G band. So this was a very important thing for us. So I put the same thing graphically here. TCN increases enormously this G band. Tetrathioefullerene donor molecule decreases this. And the width of the bands, of course, are very sensitive. They're also, width of the band also show very marked changes on donor-acceptor interaction with graphene. And the same is true of the 2D band. You remember the 2D band, which is characteristic of single-layer graphene. The sensitivity is extremely, is unbelievable. You put a little bit of molecule on this, the 2D band intensity varies markedly, and we have studied all these effects. And since then, one of my students has also measured the interaction of these molecules by calorimetry and found actually the heats of reaction in terms of when we put a TC&E, we find a very large heat of reaction comparable to that with nanotubes and so on. So electron withdrawing groups seem to open up the gap in that and so on. I'll come back to this in a minute. And as we were doing this just a few months ago, we used this technique of putting molecules. We put a large molecule like coronine with 4 carboxylates, electron withdrawing molecule with a big pi system on graphene. And you know, that not only interacts, gives charge transfer bands, all these colors, but it also exfoliates. You get single layer graphene going out with these molecules. So this is something that has just come in Chemistry European Journal a few weeks ago. I will not bother about this. I'll just tell you. Don't worry about seeing this because it will take a long time to explain that. What is another property of graphene is that given any pi system, any aromatic, which gives you fluorescence, you put graphene, the fluorescence quenching. It immediately quenches the fluorescence. Why does it do that? It is because of electron or energy transfer. And we have shown in the case of pyrene and these molecules, it is actually electron transfer. We have actually done transient spectroscopy and actually, here is transient spectra to identify graphene radical ion formation because of electron transfer from the aromatic to the graphene. I will not bother you because this, I shouldn't have put this. It will take too long to talk about it. Now, graphene has been used for many things also, for gas sensors. And recently, there's some interest in Waterloo, so I added this because of you here. We have shown that boron and nitrogen-doped graphene have probably the lowest turn-on field emission, very low voltage. As you can see, 0.6 volt, you get wonderful electron emission out of these doped graphene. We have been looking into that. Okay, and you can see the field emission from graphene. This is something very, very few weeks old. You know, you remember I take graphene oxide and just put the sunlight and reduce it? Well, you know, the minute you do that, all these graphene, which I make by a reduction of graphene oxide, or I can do the one other way. Take graphene and just slightly oxidize it by putting a little acid and shake it and throw away the acid. All of them give very nice blue color. Blue color from carbon is very interesting, by the way. You know, for those who are physicists and engineers here, the blue color made the biggest sensation in modern science in the last 20, 15 years. My friend Nakamura discovered the blue diode. You remember that? Blue LED he made using gallium nitride. Of course, he's in Santa Barbara. And he got, by the way, big Millennium, technology prize last year, which is very nice. But just like gallium nitride, This gives absolutely blue color. Well, you can see the blue color, that is the blue color. And now once I have blue, that is what Nakamura did. All I have to do is mix yellow with it, I get white light. So I want to replace all these wretched bulbs, they're awful. All the bulbs of this kind will be replaced in 5 years. Solid state lighting is coming. And solid state lighting is a matter of time. We have to reduce the cost. And that will all be gallium nitride. But why not carbon? My graphene, you see, look at the band here. I mixed it with this one with, I think with zinc oxide. Yeah, zinc oxide. And you see that band gives you white light. I hope you can see the white light to the right side. Blue of graphene, my graphene, and zinc oxide yellow band. But I said, why don't we do that? I told my student, why are we foolishly doing that? To start with, the graphene oxide itself is yellow, you see. So mix that with graphene, and sure enough, you get white light. The trouble is, you go on shining light on it. I'll skip this one. It's become too much detail. Unfortunately, mixing two carbons is also good for white light. It's bluish white light. I can show the chromaticity diagram. It is a sort of bluish white. But it is not good because this yellow color slowly gets gone away. That becomes black, when you shine light. You remember that is the way you convert graphene oxide to graphene. But anyway, this graphene oxide, I can't combine with graphene to make white light on a permanent basis. If you only want it for 1 hour, I can give you, but longer than that. See, all white light, gallium nitride. I hope you all these cheap torches available, at least in Bangalore, Burma Bazaar. That each of the little torches made in China is guaranteed for 150,000 hours. So each gallium nitride white light source, eventually when it comes, it will be good for, at least in my lifetime, I'll only need 2 bulbs in my house in my entire life. That is a wonderful way of looking at it. Well, this I don't know whether it will be good. So a lot of work has been done. We are now looking at the electroluminescence, see whether we can make a device. We have made lots of transistors and all that, looking at the electroluminescence and other properties of using the blue light of graphene. I'm only talking to you about this because it's work going on in the lab, not something that was finished long ago. So it is a lot more is to be done in this area. Well, I told you, irradiation-induced reduction of graphene oxide by XMR laser. Actually, I want you to remember that yellow becomes black. And how do you know? Imagine, to start with, this yellow solution has all kinds of carbonyl, hydroxyl. The minute I irradiate for a couple of shots, all the carbonyl goes away. Little is left. Of course, I can get rid of that by 1 or more shots of laser. It's really very clean, real cleaning the oxygen from the surface, which chemically you cannot do. Professor Carty is a very good chemist. He will know. I'm not a very good chemist who knows all the reactions and all that. Hydrazine reduction will never kill you all the carbonyls so easily. So it's but this will be very, very good. Okay, I told you this because in the last 2 weeks, we have done something remarkable. If light can transform graphene oxide into graphene, graphene is conducting, graphene oxide is insulating. Now, while putting graphene oxide, I'll put a little platinum salt, platinum hexachloride or gold HAUCl4. That also gets reduced. So what I get is graphene on which metal particles are nicely deposited. I use that as the ink now, and I can do nice patterning. This is all unpublished, by the way. I've been able to make beautiful patterning using the photochemical transformation of graphene oxide to graphene. And this is, look at this, using electron beam writing. I've written ICMS, that's the name of my lab, International Center for Material Science. That thickness of the line is 120 nanometers. I can improve on it. I'm not a technologist, I'm not an engineer, device engineer, but it can be done by a very simple idea, namely light, or sunlight, UV light, or laser can reduce, and even electron beam can reduce graphene oxide to graphene. Using that, we have done this patterning. I'll now come back to nanotubes. I don't want to forget that. My lecture is supposed to be a little bit on nanotubes. And nanotubes, exactly what we had done in graphene, when I put electron donating molecule like TTF, you see this electronic transition of graphene shift to the right, not graphene, nanotube. TC&E withdrawing molecule, that band shift to the left. Red is shifted to the left, this pink, purple is shifted to the right. So the same I didn't know that the electronic structure of nanotubes would be so sensitive to putting molecules on it. I didn't know that, to be honest, 2 years ago. And that is the case. I thought we can do many things. There are a lot of possible applications. Some of it I may mention today, because this is very nice. This is the Raman spectrum. You see, the red spectrum is the spectrum of a nanotubes as you make it. As you make it is a mixture of semiconducting and metallic nanotubes. That shoulder there, 1540, is characteristic of metallic nanotube. The red big band mainly due to semiconductor nanotube. How do you know that? Well, there is a very big, very nice paper by Ajay Sood and myself in Physical Review Letters last year to show which is which in the nanotube Raman. For those interested, you can see that. And that is the metallic. So what happens to the tube? When I put tetrathiofullerene, that shoulder becomes very prominent, that goes up. Tetrathiethylene withdraws electron, that shoulder completely disappears. That means what I am doing in a nanotube, by putting molecules, I can make a metal into a semiconductor and a semiconductor into a metal by putting simple molecular charge transfer interaction. In fact, it is nothing but an insulator metal or a semiconductor metal transition brought about by molecular interaction on the surface of carbon nanotubes. Well, to show the same thing, here it is nice. To start, it is like this. I go on putting, donating molecule, look at that, becomes like that. The same thing, when I put TC withdrawing molecule, that shoulder completely disappears at some concentration. This was a very important discovery for one of my students. In fact, he's now gone to Northwestern for a postdoc. When he did this, I thought, my God, I must do something with these nanotubes. And that has been very good. And this is the variation of the bands, how they vary with donating and withdrawing molecules. And the same with Raman bands, how they vary when I put these molecules. And we have also proved by calorimetry that metallic nanotubes interact more strongly with withdrawing TC&E molecules, and the opposite, semiconducting nanotubes interact more with electron donating molecules. And based on that, 3 months ago, we had a very major discovery in our lab. It has just one communication has come in Journal of American Chemical Society a few weeks ago. That is separating the metal and semiconducting nanotubes. That is a big challenge, by the way. One of the methods available, they are selling $3,000 per gram, or 2 grams, I don't remember, Northwestern University here, not here in the United States. I always forget I'm in Canada, and here in the US. Northwestern people, they do by ultracentrifugation. In India, anything that based on ultrafiguration, high energy, high power, in India, it all fails. So I had to do something very simple chemical thing. So I use this charge transfer idea to separate metallic and semiconductor nanotube. What we did is take the same molecule which had separated the layers of graphene, tetracarboxylate of coronium, very good pi system. I put that in a mixture of nanotubes which are both semiconducting and metallic species. And what it does is it preferentially gets stuck to the metallic nanotube because of the electron density. And the metallic nanotubes precipitates out under the right corner. And then you take the spectrum. The precipitate has only metallic nanotubes. The precipitate start with have metallic nanotubes, that little peak, and these two semiconducting peaks. This is the optical spectra. The precipitate has only metallic nanotubes. The solution has only semiconductor nanotubes in one step. And you can also see in the Raman band. Raman band pristine has a mixture, but the precipitate has mainly metallic species. From solution, only the semiconducting species. This, I think, is a fantastic thing for an old man like me, because do a simple reaction like that and give you, people have been trying to do this for so long. It's a very important engineering application here. So for those who are interested in sensors, for good sensors, you normally require a good semiconducting nanotube, not a metallic one. But that's when we should show maximum variation, resistivity, and so on. Or you may need, for something else, metallic nanotubes, then you can do that by a simple chemical process. This, I think, is a very nice discovery by a student of mine. Okay, I'll not bother with the Well, I also told him, is there not way of directly just make a tube, and as you make it, it is only metallic. It is one of those things. In chemistry, there are no reasons, sometimes no rhyme, things work. That is why chemists are different. You see, we are not physicists, we are not, material scientists are also. You are looking for the logic of everything, you will never make a major discovery in chemistry. You would have that gut feeling. Same with material science. Major discoveries will come by gut feeling, not by theoretical analysis. Then you can do theory later, which I do always. After doing the experiment, then find theory. And very few theories have predicted things like separation of metallic and semiconductor. I'm nothing against it. I do, but all my papers have theoreticians as co-authors because I need the explanations. But here, one of my students actually was doing arc discharge to make nanotubes, single-wall nanotubes. He just put iron pentacarbonyl in the gas phase, just like that, along with the gas discharge. And what he got was all the nanotubes we picked on the surface of this chamber were only metallic. You see, the only metallic nanotubes in one-step synthesis. So this is another thing. You can see the mixture would be like that. 3 transitions, 1 metallic, 2 semi. This is the only metallic transition in the presence of iron pentacarbonyl. I'm coming to end of my lecture. I would like to talk about what I'm doing in the last few weeks. See, graphene is wonderful because it is carbon. What an exciting thing. But if you remember, fullerene was synthesized in 1990. Immediately people said, why should it only be carbon? Why can't I have fullerenes made of inorganics? My very good friend in Weizmann Institute, Rashef Tane, immediately took molybdenum sulfide. Why not I make a fullerene structure out of molybdenum sulfide? Because it's also a layered structure. Sure enough, he did that. So did we. I'll just show you some of our fullerene structures. This is done by my lab. This is my hafnium sulfide fullerene. And niobium sulfide fullerene made by Tene. These beautiful fullerenes, hyperfullerenes, were made at that time. Well, you can see the papers are all 2002, 2004, long ago. Not that long, long enough. But one of the things that we did in Bangalore, and also Reshap did a little bit, is why not nanotubes of inorganics? After all, why only carbon nanotubes? So we, in fact, I have a very good friend of mine, a student of mine, Manasi, she did a fantastic job of making all kinds of inorganic nanotubes. We have done boron nitride, all kinds of sulfides. For those interested in this area, this is a very good area for young people. I'm telling you, you want to do research, work on inorganic nanotubes. The phenomena, properties of these materials have not been investigated, unlike carbon. If I were young enough, I would have done it, but I have not enough time to do that now. But a lot of work can be done on the engineering applications, physics, chemistry, a number of aspects of inorganic nanotubes. Carbon nanotubes, as you know, already is too crowded, so it's not a good area now. So we made all this. For those interested, the synthesis of this, just December 2009, I have a perspective article on this in Advanced Materials for those interested to get into this area. Well, the same thing, why not graphene, right? Why not inorganic graphene? That is what I told myself. One sheet, why only carbon? Why not boron nitride? Why not molybdenum sulfide? So one of the best simple ways we did a few months ago, it has just come in ACS Nano, is take urea and boric acid, heat it at different temperatures. We have been able to make, you can see the height, I don't know whether you see the AFM height, that height is exactly 0.3 nanometers, 1 layer of boron nitride. I've been able to make, I hope you can see the height, 0.4 nanometers, single layer boron nitride. So I've been able to do that. Boron nitride, single layer graphene equivalent, and don't worry about that. And look at these beautiful pictures. I just want to see that, admire it. You know, this is a few layer boron nitride. I can count it 1, 2, 3, 4, 5, 6 layers there. And here some of them are 1 or 2 layers. This is the beautiful atomic resolution, single layer boron nitride, where every atom can be seen. I can measure all I need is a foot rule, inch scale, and I can measure the distance between atoms. Exactly what I do, you see? This is a high resolution, aberration-free microscope. And so you can get this beautiful image, and you can measure the boron-nitrogen bond distance, boron-boron, all that. And this is a single layer boron nitride. This is something we did recently. And we have also done, we'll forget that, surface area, we have done functionalization. Of course, as usual, I told you, always I do theory. We have done all the electronic band structure of boron nitride as a function of number of layers. Will not bother you. But we have recently made a boron nitride nanopans. Nice pans, nanopans, that the diameter is only 40 nanometers. You can see the pan, if you go, the edges go up, and in the center it comes down. It is a very nice pans can be made. I'll describe, not worry about the description of the pan. Molybdenum sulfide, you remember we made fullerenes of that. Why not graphene? So we started doing this, first taking the same Scotch tape technique. I want to see how sometimes you fail. And then and I could get down to 6 layers. I went on seeing changes in Raman spectrum. I stopped it there. Then I thought, well, let me go to chemical method, not Scotch tape. But since then, another student of mine actually has done Scotch tape single layer. And I found completely new transitions in the Raman spectrum. Some new physics and new theory has to be done. Single layer molybdenum sulfide, what happens in Raman spectrum. I will not talk about that. However, we found 3 reactions by which you could make few layer graphene. It has come in Angewandte Chemie. It's a very important journal in chemistry for those who are not chemists, 2010. And how do you know that? You see, this is the 002 reflection of MOS2. The minute I make singular 2-layer molybdenum sulfide, that reflection goes off. 002, okay? And of course, Raman spectra also changes. I will not be talking about that. It takes time. And you can see this is a 2 or 1-layer molybdenum sulfide with every atom shown there. Of course, we have done again band structures of molybdenum sulfide as a function of number of layers. As I told you, in everything I do, we do with my theoretical science or physics friends. They have done the calculations and the electronic structure. The same thing we have done on tungsten sulfide by chemical reaction. See the 002 reflection going off. And again, over here you can see. See, this is the electron microscopy. You see, there are only 2 layers, 3 layers, 2 layers, 2 layers, 3 layers, 2 layers, 3 layers. And this is the high resolution tungsten. So inorganic analogs of graphene have been made in our lab successfully. Well, we have made other molecules which I will not talk about it. We have made a new compound called BCN. Instead of carbon, instead of boron nitride is BN. Graphite is carbon. Why not 1 boron, 1 carbon, 1 nitrogen? We have succeeded in doing that recently. I will not talk about that. We have studied, these are just the theoretically calculated structures. We have done a lot of experiments. This is a very high surface area, BCN, up to 2,000 meters per square meter per gram, and with very high carbon dioxide uptake. In some of my BCN samples, 100% I get carbon dioxide inside. It really sucks carbon dioxide. I'm doing a lot of work on that. I'll not talk about that today. I'll end this lecture with this slide. What is it I'm doing now, just now? I think it's very important for all of you to know. You know, there was a paper in Science a month, maybe several months ago. You can put hydrogen plasma on graphene. It picks up hydrogen. And they say that hydrogen is not stable. So what we have done is, we have done chemical reduction of graphene. You see, completely if you reduce graphene, as you know, for every carbon there will be 1 hydrogen. Carbon has an atomic weight of 12, hydrogen is atomic weight of 1, so it will be 8 weight% is the maximum you can ever get. If I get 8 weight%, which is reversible, I would have solved all automobiles or all cars can be run on that. That is what Department of Energy wants, 6 weight% storage of hydrogen in a solid to run automobiles. Now, we have got up to 5.5 weight% on graphene, hydrogen. What is amazing is that comes off. That hydrogen which forms CH bonds, as I follow the infrared spectrum, the CH band around 2,900, 2,850 reciprocal centimeter bands, as I go on heating it up to 400, all the hydrogen comes off. And that has been very heartwarming for me. Here is a wonderful reversible hydrogen source which comes off just by warming. I don't know whether technologically it will work out. So in the meantime, I asked this student of mine who works on all these optical, why don't you put infrared, ultraviolet or laser? He put ultraviolet or laser, my God, that immediately pulls out hydrogen. So I'm now up to 5.5 weight% hydrogen in graphene, which is reversible. Is it going to be a storage for hydrogen? Look, I've not yet said that. Why not? Maybe. I'm a bit hesitant to say it will be a storage. It is like a storage for hydrogen, which is reversible, with almost 5.8%. I'm very proud of that work, actually. I've not yet published that. I've not talked about it. It's the first place I've ever mentioned this. This is not something, but don't write up papers, any of you guys. It's very dangerous. If this is true, I'm very pleased. Graphene will be probably a good store for hydrogen. May not be good for cars yet. But 500 degrees is nothing. Today I was talking to a friend of mine in the chemistry department here. The engine in a car, near the engine the temperature is about 800 degrees. when the muffler, when the gases come out of the muffler, near that is about 500 degrees. So removing hydrogen even up to 400-500 degrees is not a big problem. The cars have that heat. But I want to use that hydrogen for running the car, don't forget. There's a slight difference. So anyway, that is where I'm working on. I'm doing many other things. I'm actually put halogens in graphene, what happens to halogens. I'm not going to bore you with all that. It's been a very exciting thing. One thing about science, I find as I'm getting 77 years old now, as you go on doing it, you become younger and younger. Particularly when graphene came, my age really came down. I mean, I really tell you, it's like a toy for a child. Graphene has been a wonderful toy. So Norman, every day I find new toys. I mean, there's a very wonderful life. And I think science itself is so exciting because of that. Keeps you young, very happy. I had no time to pull down anybody, talk bad of anybody, like all my colleagues do, spend hours on it. I have no time. Writing papers takes so much energy, and writing books. So I want to thank my wonderful students who have done a lot of work. Many of them are postdocs now, and some of my faculty colleagues who have collaborated with me in doing theory particularly. And thank you. You want questions?
Questions?
Sure, okay.
Professor Rao has indicated that he'd be prepared to take a few questions for Ronnie.
Yeah.
Yes?
Yeah.
Aipen?
For the chemical way to produce graphene,
Chemical?
chemical way to produce graphene oxidation reduction, how you control the thickness or how you control?
Wait a minute. See, if you take graphene oxide, if you do mechanical treatment or sonication, it becomes single layer in solution. And you reduce it, you can get single layer reduced graphene oxide. But it will be in solution. But what you do is take a solution and disperse it on a solid substrate, you can get that. But it won't be exactly single layer when you put on that, but you can make it single layer. We have done that. But you cannot take it out, because when you take it out as a solid, it becomes graphite. So you have to always keep it in solution. But unfortunately, this reduced one is not real graphene, because there are some oxygen functionalities always. That is why my laser method is very good, because it more or less gets rid of most of the oxygen functionalities. When I take the same graphene oxide and irradiate it, most of the oxygen goes off. That would be better way than reducing it in solution. The same solution, use laser radiation, would be much better. But you can get nearly single layer.
So if
Huh?
surfactant,
Surfactant, yeah. Surfactant?
yes.
You don't need surfactant for this.
But if you large scale still have this problem, right?
No. Well, you see, you can never keep single layer graphene separately in a bottle, because it forms graphite usually. So you will have to make a solution always, or do mechanical exploration. When it comes to 2 layer, 3 layer, 4 layer, you can make it and keep it in a bottle. There's no problem.
Yes. David?
Thank you very much, Professor Roth, for a nice talk. I have a question about the radiation-induced reduction of graphene.
Yeah.
So, as we all know that matter cannot be created, since we need electrons from some matter to
Sure.
transfer to graphene oxide.
Yeah.
And to be more specific on where.
Well, light-induced, we can actually use catalysts like zinc oxide and TiO2, which I didn't talk about it, which actually gives electrons, but even otherwise, I had shown the mechanism. There is a photochemical reduction that can occur. In the photochemistry, you can use light and reduce. And that's the one that creates excitons, and you will get separation. Then that's what happens. You create excitons and then reduction and so on. I gave the mechanism. There is no matter creation, no creation of matter here.
Yeah, Dr. Rao, you showed light emission spectrum from graphene.
Yeah.
Is that graphene a solid layer or just a
Both ways. You can get a solution as well as solid. That what I showed you was there was one spectrum in solution dispersed in a DMF or some solvent. Another one was a solid. Both can be done.
So the solid, how thick is the solid? What is the thickness?
Maybe a micron, half a micron. Fairly thin. Yeah. Well, most of them, a few 100 nanometer layers is what I study normally. Maximum of a micron.
And what is the stability and lifetime of these?
We have done that. Well, the quantum efficiency of this blue light, many of them is up to 5%, is not so bad, 4%, 4 quantum efficiency. So that is what I don't know. Next year I'll tell you. Thanks, sir. I hope it is stable, I think. I don't know. Yeah. That's true. No. Good transistors have been made by graphene by a number of people in Amsterdam, also a number of people here, using single layer graphene without any problem, which is ambipolar. It's quite stable. There is no problem. Leakage is also not a problem. Where did you say it is a problem?
You said that it was difficult to turn it off. Turning it on was easy, but turning it off.
You are talking about my work on field emission, or are you talking about transistors? Well, I didn't find any problem in turning off. I do not know, actually. I'm not aware of the difficulty. Maybe it is. You see, I'm not a very good I'm not an engineer. I make my transistors only for certain purposes, and I'm not worried about these characteristics. I must look it up, actually. But I do make transistors in the lab. That is a different thing. But for a particular purpose, for a sensor or some other purpose. But there I have had no difficulty.
Many interesting properties of graphenes come from the hexagonal structure of graphene. Those should be made from other materials. Does they have the same structure?
Yeah. You see, molybdenum sulfide has a trigonal prismatic coordination, but boron nitride has exactly the same structure as graphene, 6-membered rings.
So does it mean that we should expect similar properties?
Oh, well, nobody has studied them. I'm waiting for people to do that, except that boron nitride does not have as many carriers as graphene. So, you see, if you remember, graphene single layer is a gapless material, where boron nitride has a gap, a small gap, even in a single layer. So, it will be sort of a semiconductor or insulator, unlike graphene, which is a gapless material. A 2-layer graphene or 3-layer graphene become insulating, sort of semiconducting. Boron nitride is worse than that. Boron nitride is a very bad insulator. So you can't make it very conducting. That is why we are making BCN, see whether that would be electronically more interesting than BN or carbon. But BN won't be. Molybdenum sulfide, electronic properties have not yet been studied. This is what I'm saying. There is so much has to be studied in inorganic layered structures. Most of it is synthesis, a few gross properties like what I do, some very good, in fact, I have no time otherwise, optical, hydrogen storage, electrochemical properties, batteries, a number of possible applications of inorganic nanotubes, and so on. And also lasing action, many of them are good lasers, zinc oxide, for example. Just now setting up a lasing action lab in my lab to study lasing action. But many other things can be done. The electrical properties alone properly not been studied. I know that. Yeah, buckyball was done only by Reshef Tene in Weizmann Institute in 1992. Reshef Tene in Weizmann Institute did it in 1992, buckyball. No. 1997, even Fullerene had not been made. 1985, Fullerene was discovered in a mass spectrum. MOS2 Fullerene was not known in 1990s. Well, that was not very good. They didn't characterize it. There was one paper, they didn't know how to characterize it. Then there was no AFM.
Yeah, so my question actually is, how is your material different from that?
I don't know what they did. I've seen that 1 or 2 papers. I can characterize everything I do. And I will refer to those papers. I don't know how good their samples were because I don't know what the thickness was because they didn't have atomic force microscopy or transmission electron microscopy. You see, they would do X-ray diffraction or show something. That is not enough. X-ray diffraction will not show a peak even if there are 4 layers. I mean, it's very difficult to characterize without diffraction.
Pre-Panopticus was looking at Warren peak shapes in the MOS2 type systems there. I think they were down to a few layers. And my question really was, how do your properties differ from the...
I don't know. I've not done much on properties. As I told you, a lot more has to be done. In fact, one of my students is now, they say, In Israel, they have set up a huge company for tribology, for solid-state lubrication, and they're all saying this MOS2 single layer may be very, very useful in that area. I don't know. Somebody has to do that. I have a very close friend who was from, in Switzerland, who does this photovoltaics, Gretzel cell. He wants to use my MOS2 layer in his photovoltaics. I don't know how he will use it. I have not yet discussed with him. This is only a few months old. I hope a lot more work can be done. I've not done much yet myself. Yeah, sure.
Short question. The chlorine-induced precipitation of the metallic versus the semiconductor graphene was quite interesting. What is the critical turn-on? What is that factor that really causes the
Well, it is the pi. There are two things that go in. There are two things going in for coronene carboxylate. Mere coronene would have given you only pi interaction. But with having tetracarboxylates, it also electron withdrawing. So an electron withdrawing molecule is attracted to metallic nanotubes, which I had shown earlier, C.N.R. So it is not only electron withdrawing, it is also favored by pi interaction. That is why I think it is working better. Charge transfer, there is charge transfer. There is a charge transfer band between coronene tetracarboxylate and graphene. There is some charge transfer. That's what happens. It only happens preferentially in that.
One last question back here, and I think we'll have to...
Yeah, some work has been done, even we have done it. Nothing exciting has come. As you know, there are many predictions which I didn't talk about. For example, if you dope graphene in a particular way, people have predicted superconductivity in graphene. Nobody has done that. In fact, some young people, I feel like doing it, but I don't like such things. I have not done it. But magnetoresistance we have done. There is a weak magnetoresistance, very weak, very small.
Well, one last one.
Yeah.
I'm working on similar areas. You also have many questions.
Yeah, well, why don't you come to Bangalore? You can decide all the...
I'm very interested in the separation of metallic and the semiconductor field. I know most people using the dielectrophoresis.
I know that.
So the chemical
That's what Northwestern method, Northwestern University, they use either dielectrophoresis or centrifugation, high-speed centrifugation.
but for your chemical way to do that, the chemical molecule you introduce to semiconductor field, and do you check if they have big impact on the
I remove it. I remove after that. I have to remove it to get back my tube. I remove the molecule on the surface. By heating it, it goes off, or by washing it and heating both. Yeah.
Well, I think you have gathered from Professor Raman Spectrum's enthusiasm for his work that he really enjoys his chemistry. So I've got a suggestion for the title for your talk.
Yeah, next
Having
year.
fun with graphene. Let's thank him very much.
Okay.